Hello friends, welcome back to our channel STM Mechatronics. So in this video we will see how to interface a load cell with STM32 F103 C6 or C8 controller. Right. So first we will see our simulation is working properly or not, so that I can walk you through the code and then we will understand how the code works. So this is very simple project. We have connected one load cell. Okay. So if you go to the placement, type load cell, okay, you will be given a general purpose load cell sensor. You can click OK and you can place the load cell over here. Okay, so I have already made this schematic. Then we can go to edit properties. See, here we can see that the percent of steps the step percent that we increment, the full scale percent that is incremented, and the bridge resistance, what will be the resistance of the bridge. Okay, 2 ohms of the bridge, so that is already given over here. So if we consider that 350 ohm, 350 ohm, 350 ohm, so R1, R2, R3 and R4 both will have the same value, that is 350 ohm. Okay, now if you consider that 350 ohm, 350, so R1 plus R2, that is, this will be like 350 divided by 700, so it will become 1 half. So at this arm, like the voltage at this arm will be 5 divided by 2, that is 2.5 volts. Okay, if you go and place a voltage probe over here and another voltage probe over here, okay, so if we can see that both voltages, okay, will be equals to 2.5 volts. Okay, so whenever we are going to increment the values, okay, now you can see that there is voltage change. Right, now you can see that at 100% it means we have increased the resistance to full. Okay, so we will get 2.505, and here we will get a lower voltage, that is 2.495. okay, now I'll lower this volt. So the load cell works like in a way that we have two arms of the resistance divider network. So in the one arm, the one resistor, that is the load cell resistor, that will be variable depending on the pressure that we are applying or the load that we are applying. Okay, so its resistance will increase or decrease. Okay, now that increase or decrease in the resistance will create the slight change in the voltage. Okay, in the voltage divider arm. Now that we have that voltage that we have given to the amplifier. Okay, now the amplifier voltage we have given to the ADC of the STM32. So we will go first. In this video what we will do is we will interface only the ADC. Okay, we will get the ADC value and then we will display that ADC value on a UART terminal. Okay, now for that what we will be needing is we will be needing first an ADC input. So we have configured PA0 as ADC1 input 0. Okay, and for displaying the values on a UART, we are configured that we will go over here connectivity. In the connectivity we will go to UART and we will select it. We will select it as asynchronous, and here in the baud rate we will keep the baud rate as 115200. Okay, so whenever you are selecting the mode as asynchronous, you will be able to see that PA9 here, PA9 and PA10 will be selected as UART1 TX and UART1 RX. Okay, now we will come over here, we'll come to RCC, and here in the high speed clock HSC we will select it as crystal ceramic resonator. Okay, so these two pins will be used for external crystal oscillator. Okay, now if you see, we have selected our device as STM32F103C6TX. So whenever you are selecting a new project or whenever you are creating a new project, you can go to the file, new, STM32. You can type here as STM32F103C8 or C6. In your case, you can select it as C8. Then click on next, give the project name, click on next and finish. Okay, by creating that, you will come to this window. For our simulation, we have taken it as STM32F103C6TX controller. Okay, that's why it is displayed. And in our simulation also, we have taken it as STM32F103C6 controller. Okay, so we'll come over here. Yes, now coming to this, we are not configuring any LED pins for this project. Okay, this is simple load cell project that we are displaying the value on USART. So we are not going to use any LED indication for this. Now coming to the ADC, we have to do the ADC settings also. Now by default, our IN0 ADC1 IN0 channel has been selected for ADC input. Now in the configurations, we'll have to come over here. We have to select the mode as independent. Then data alignment will be right aligned. Okay, then scan conversion disabled, continuous conversion is also disabled, then discontinuous conversion is also disabled. You have to keep these settings as I have shown in the video. Okay, now ADC regular conversion, enable regular conversion, enable number of conversions. Whenever we are giving the start of conversion pulse, it will be of 1 conversion. Okay, external trigger will be regular conversion lodged by software. So whenever the ADC start command is given, it will start the data conversion. So analog data will be converted into digital. Okay, then rank 1. So channel 0 and sampling rate is 1.5 cycles. Okay, so we can change these cycles also. Now coming to clock configurations, here we are going to use the internal HSI clock, that is internal RC clock. So we have given that HSI clock, that is internal RC clock, to PLL clock source, PLL source mux. We have multiplied that PLL source mux by 2. Okay, now PLL clock source, it is multiplied by 8, that is 4 into 2 is 8. So we have brought our system clock to 8 megahertz. We can do like that, we can increase the clock frequency to 72 megahertz also, or 36 megahertz also, but we cannot go beyond 72 megahertz maximum, and ADC does not support above specified, that is so if you see, ADC1 and ADC2 does not support the clock frequency above 14 megahertz. That's why we are keeping it as only 2 right now, for simple conversions. So if you see, our ADC will be sampled at 4 megahertz. Okay, the ADC clock is of 4 megahertz and it will be sampled at 1.5 clocks. Okay, so 4 divided by 1.5, that will be the ADC clock. Now coming to here, pin out and configurations, will come over here. Now we have set up everything. We have set up our ADC pin, we have set up our USART with the baud rate of 115200. We have set up the external crystal clock also. Okay, though we are not going to use it, but we have set up, because on the blue pill board we are using external clock. Okay, external crystal. So it is important to configure it like for the external crystal clock source. Okay. Now click on the device configuration tool code generation. it will create the basic configuration needed for our program. So what it will create, it will create the system clocks configuration settings, then GPIO settings, ADC settings, and UART settings. Okay, now coming to the top of the program. So I have added few functions over here. That is, we are going to display the values on the user terminal, right? So serial terminal. For displaying the ADC values on the user, we have added this function print character. Now we have taken one variable. Okay, this is local variable, not static, not global. This is local variable. Okay, so its value, we have taken its type as uint16, because our ADC is of 12 bits, so maximum 16 bits will be required to take the ADC value. Okay, we cannot store it into 8-bit value, so maximum 16 bits, minimum 16 bits will be required. So that's why uint16, the variable is of uint16. Now coming over here, see, we have given few simple commands. ADC start, it will start the ADC conversion, or it will configure the ADC. Then HAL ADC poll for conversion. Now this, like, we are using the ADC into polling method. Okay, so whenever we are going to use this command, the internal software will give the start of conversion command to the ADC. Okay, now once that is done, we will wait for the end of conversion, and we will read that value, ADC value, from channel 0, ADC1 channel 0, and then we will give the command as stop ADC. So no more conversions on that ADC again. Okay, now we have given the command as print character, and we have given the delay of 50 microseconds, 50 milliseconds. Now coming to the print character function. Okay, so here we are. Now on UART can or serial terminal can print the ASCII characters. So to print the ASCII characters or print the ADC value into ASCII characters, we will be needing an array, character array. So uint8, you can take it as uint8, or you can directly take it as character array. So character numVar. So we have already initialized it as 6 zeros and 2 special characters, that is \r/n. So whenever we are printing, every time we are printing the ADC value, along with the value, we will also be printing these 2 characters. It will take us to the new line and start of the first new line. Okay, so carriage return and new line, these 2 special characters will also be included in printed with this. Okay, in this array. Now coming to the array, that is uint16 array size. Now size of array, so whatever size we are defining over here, okay, it will be taken. So size of is a standard function. Now we have taken uint8 i5. Why we have taken i5, I equals to 5? This is a local variable, so we are going to do the iteration to print it or to go through 5 digits. Basically we are going to print the 5 digits only. So starting from 0, it will be 6, right? Now we will come over here. So while numVar, so whatever variable we are passing, or whatever ADC value we are passing, is not equals to 0, till this loop will continue to execute. Now we will store the value into this character array. So now I value is 5. Okay, so we will be storing it at this location. Now I value, right, we have taken the ADC value modulo 10. So we are dividing it by 10, and whatever remainder, we are adding 48 to it. So we are converting it to the ASCII character. Okay, now once this conversion is done into ASCII character, we are storing it at this location. So we are starting from the lowest digit. Okay, now numVal, whatever ADC value that we have passed, right, we will be dividing it by 10. Now we will decrement the I++. So next digit will be stored at this location. The next in the next iteration, next digit will be stored at this location. In the next iteration, next digit will be stored at this location, and next to that iteration, the digit will be stored at this location. Okay, so likewise this while loop works. Okay, now coming to this character I equals to this, so numVal modulo 10 plus 48. So each time we are dividing by 0, so whatever the final value, we will be dividing it by 10 modulo 10, and we will be adding it to the 48. That is, we are converting this into ASCII variable. Okay, after completing the conversion, so after converting the digital number into the ASCII string, ASCII character string, we will be directly printing it to the UART. So we have given it like HAL UART transmit. On the UART1, our this array, character array, then size will be of the character array, and this is the delay given at the end of the character array. Okay, again 1 millisecond of delay we have given, we have provided. Now we'll see, we'll compile this, we'll build our code. Now you have to remember that we are going to change one settings. Okay, so right click on this, go to the properties. Okay, once you come to this place, on C++ build, expand this, go to the settings. Okay, you will be seeing the settings tab. Then here MCU post build outputs, click on this and tick this box, convert to Intel hex file. Click apply and close. Now we have to build our code. Here you can see that we have 0 errors, 0 warnings. Okay. Now come to your simulation. So here you can see that today is 17th February. Today is 17th February, and on 10:55 p.m. we have built our code. So we will load that hex file and we will load our code into our simulation, right, into our microcontroller. Now see, one more settings that I have to show you. You go to the design, configure power rails. Here ground, in ground VSS and VSS-A, these 3 nets will be here in the ground. In VCC, VDD-A and VDD, these 2 nets, and the voltage level will be of 3.3, and in VEE the voltage level will be of 0. Okay, now I'll remove this 2. I'll start the conversion. Now if you can see that this is 0.091, okay, or 0.092. So 0.092, the minimum voltage that our ADC can detect is of 8 millivolt, or I can show it to you that 1 divided by 2 is to 12. So we'll do like this, 2 raised to 12. Okay, because our ADC is of 12 bits, that is 4096. So we will do 1 divided by 4096. Okay, this will be equals to 0.0002441. Okay, now maximum voltage that we will be providing to over here will be of 3.3 volts. So we will do is 3.3 volts. So we will get it as 8056. Okay, so if you can see that minimum voltage that we can detect is of 8 millivolts. Okay, so if I multiply this by 1000, it will be of 0.8 millivolts. So let me increment this. Let me take it to the fullest. So yeah, so at 100 or at the maximum scale, the maximum voltage that we will be providing will be of 3.3 volts. Okay, so now we need to check that at zero level what will be the voltage. Okay, so here we can do like that, 1 divided by 4096 will be the maximum value, okay, into 3.3 volts. So 1 divided by 4096 into 3.3 volts. So the minimum voltage that our ADC can detect is of 0.8 millivolts. Okay, so whenever we are at the zero scale, our output is of 0.92. so if we divide it by 0.92 divided by 0.0008, we should get the value as 1150. So we are approximately getting the correct value, 1141, isn't it? So we are getting the correct value. Now what we will be multiplying the values also. Okay, now if we want to print this scale into the zero, or the load cell value to the zero, we will be doing that multiplication. Okay, so the minimum voltage that our microcontroller can detect is of 0.8 millivolts. Okay, so that is 0.8 millivolt will be the step size whenever we are applying the full scale range of 3.3 volt. Okay, now if you change the voltage level to 5 volts, it might be different, but the maximum voltage that we can give to our ADC is of 3.3 volt. Okay, so if you see at 3.3 volts, we are getting the maximum step count, that is 4095. So it is correct. Okay, now we can decrease it, and you can see that whenever we are decreasing it by step, we can see the gradual decrease in the ADC value also. So here I am decreasing it, we can see the gradual decrease in the ADC value. So now I am going to increase it. So here you can see that the values are incrementing. So this way our load cell simulation works. Now why we have used this AD620 is, so this is an instrumentation amplifier. We have provided a R3, that is gain. So if you refer to the AD620 datasheet, it is pretty much simple. Okay, so one end of the load cell, that is variable end, that we have connected to non-inverting terminal of the op-amp instrumentation, and another voltage divider network, okay, that we have connected to the inverting. Okay, and this is the feedback R3, or this is gain resistor, that is of 150 ohms. Okay, So whenever you are going to select the value appropriately for this R3 resistor, the gain will be incrementing or decrementing. So the formula will be available. If you search the datasheet, you can easily get the formula. Okay. So this way our simulation works. The code is pretty much easy. If you have any doubt in the code, you can ping me. Okay, you can ping me on mail, or you can send me query on my WhatsApp number. So thanks for watching our video. So if you like my explanation, share this video with your friends, hit on like and subscribe to our channel. Thanks for watching this video. We'll see you in the next video.